In section 8.3, they've got several different applications, sort of physics, engineering type applications. And I don't really want this to be a physics section. I want it to be a calculus section still. I'll leave the physics to your physics instructors. So we're just going to focus on one particular application, and we're going to try to keep the focus a little bit more on the calculus than on the physics. So we are going to look at hydrostatic pressure, which is just the fancy name for as you submerge something in water, the pressure on it. So when you dive down to the bottom of the pool and your ears start to hurt. Right, hydrostatic pressure. Okay, so let's consider some hydro. Let's see, we need blue for hydro. So there's some hydro, some water. And let's say you've got some sort of shape submerged. And just to keep it simple to start with, let's just keep it a rectangular shape. And we want to talk about the total pressure on this shape. And this is, by the way, the practical application here often is like sort of figuring out the pressure on the wall of a dam or something else that's holding back water. But so let's imagine that this thing is let's say 10 feet wide and 5 feet tall, and that it is submerged already, or the top of it is submerged at a depth of 4 feet. Okay, that's going to be enough for us to set up the integral, but before we do that, we do need to talk physics just a little bit. So we need to say here that the force, hydrostatic force, is the pressure times the area. So let me write that out. Pressure times area. And the pressure by itself, we need to unpack that a little bit more because the pressure depends on the depth, of course. And the pressure is the density times the depth. So I guess we need to unpack that. So let's see, let's write that out as density times depth. And yeah, I don't want to get too much into the physics of it. This is actually weight density for those of you that care about that instead of mass density, but I'm going to give you the constants here in a minute. So the weight density, if we're dealing with water, which we're going to be for all the problems except for one, the weight density of water in metric is approximately 9,800. So that's in metric. And the weight density of water in imperial is 62.5. So I don't want to get too much deeper into the density and the physics of it than that. And I just want to say that our basic idea then is going to say, since it depends on depth, let's look at every portion of the shape that's at the same depth. So we're going to look at a strip, a rectangle of our submerged object, everything that's at the same depth. That will allow us to talk about area. And when we talk about pressure, we'll also be able to talk about depth. So really, our overall integral here for hydrostatic pressure is going to look like density times depth times area. So let's take a look at how that would actually work for our little shape that I have drawn over here. Now, one of the challenges that you're going to find in this section is setting up the coordinate system, like choosing where x, y, like where the origin is, in which direction x goes. And I know as math students, we always feel like, well, the origin's at the origin and the function depends on that and everything, but this is a physical situation. We just need to set up coordinate system that works for us. So let me do this. I know one of the things that is going to be part of my integral here is depth. So let me set up my coordinate system like this. I'm going to put the origin right there. And I'm going to let x go that way. So positive x is going to be the depth. So in other words, when x is 2, that means I'm right here at 2 feet down. When x is 4, I'm at 4 feet down, and I'm just at the top of my red wall. And when x is 10, I'm at the, when x is 9, it should be 4 and 5. When x is 9, I'm at the bottom. So I'm going to set up my coordinate system so that it is centered side to side on my wall, and so that x actually represents depth, which makes my depth at least easy to write. We'll see how the rest of it works out. So let's see if we can set up an integral here. I didn't actually give units on my 4 and 5 and 10. Let's make these feet just for the fun of it. Okay, so our integral. Our object is we're integrating from a depth of 4 to a depth of 9. Since we are in feet, the weight density here is 62.5. Because of the way I set up my coordinate system, depth is measured strictly by x. So far, so good. Now we just need to talk about the area of one of these blue rectangles, because that's what we're adding up, is all the blue rectangles that cover this red shape. So the area, I should point out, now that we've made x what it is, that this side of the rectangle, guess what, is dx. And now we really just need an expression that talks about the length of the rectangle. And the length in this case is constant. It's really nice. It's just 10. So it is just 10 times dx. And just like that, the integral is set up. The setting up of the integral is always the hard part in these. Usually the hard part, I should say. They're not above giving you like a u substitution or something for your integration, but mostly the setup is what's going to challenge us here. And again, the integral is easy to work out here. I'm going to multiply the 10 by the 62.5 and pull that outside. So I've got 625 integral from 4 to 9 of x dx. And that integral is, of course, 1/2 x squared. From 4 to 9 with the 625 out front. Plugging in 9 and plugging in 4, we can finish this off without too much trouble. So it'll be 625 times 81 halves. Minus 625 times 16 halves times 8. And I'm not even going to finish crunching that out, but that's the basic idea for setting up hydrostatic pressure. So let's take a look at another example, maybe one that's a little bit more complicated than just a rectangle. So I think I want to keep my formulas. I did mention that every problem in the homework is water, except for the last one. The last homework problem is something is submerged in gasoline instead of water. And they give you it's not 62.5, but it's in standard units, and they just give you the weight density. So you'll be fine with that one too. Okay, so let's get a different shape going that's submerged. And this time I'm going to take a trapezoidal. There it is. A trapezoidal wall sort of thing. And let's say this time it's submerged. 20 meters down. And let's say the top of it is, what does that look like? About 60 maybe? And the bottom, more like 100. Okay, so let's set up a coordinate system. Oh yeah, and I said these are meters, right? So let's set up a coordinate system. And I think once again, I'm going to put my axes right here, and I'm going to let x be depth. It's not the only choice, by the way. Maybe the next one will set up the axes in a different place, but it is convenient to make x measure depth, unless there's a good reason to change that. Okay, so let's set up our integral. It is weight density first, which for metric is 9,800. Depth in my coordinate system is just measured by x, again. And then I want to talk about the area of one rectangle that's all at the same depth. And again, the area is just dx times the width. So now I do need to figure out the width. And obviously the width is different at different places through this shape. And we need to write it in terms of x, right? Because that's what our integral. We're in x land. Speaking of which, let's go ahead and set up the limits of integration. So we start at 20 meters deep. And, I didn't tell you how tall this thing was. Okay, let's get that in here. Let's say this is another 50 meters. Sure, just making that up. So we started at a depth of 20 and we finished at a depth of 70. Okay. So the only thing left now is to say I need an expression in terms of x for the length or the width or whatever you want to call it of this rectangle. There's a couple ways to set this up. The way that I prefer to do it is just to recognize that since the sides are straight, the width of this rectangle is going to be described by a linear function. And I just like setting up a couple points. Say when the depth is 20, how wide is my rectangle? So let me put that over here. When the depth is 20, the width of my rectangle is 60. And when the depth is 70, how wide is the rectangle? So at a depth of 70, the rectangle has a width of 100. Sorry, it's not a rectangle, trapezoid. Oh, no. The rectangle. I'm talking about this rectangle right here. The little approximating rectangle we're using, which matches the width of the trapezoid. Anyway, yeah, so the width of our rectangles based on the depth is a linear function that goes through these 2 points. So if I could just write the linear function that goes through those 2 points, I'd be good to go. And you know that linear functions are slope and intercept. If you can figure out the line that goes through these 2 points, that's all you need. I just prefer to think of it as slope. So change in y over change in x. So that's 100 minus 60, 70 minus 20, it's 40 over 50, it's 4/5. And then I just need to plug in one of these points and make sure that the b fits. I'm getting spam. Let's see, so maybe I'll just plug in 20. So yeah, let's figure out the b. Hope this isn't too much detail. I know you know how to find the line that goes through 2 points, but so that's going to be what? 16 plus b, that was plugging in 20, and needs to come out to 60 when you do that, so b is 44. Okay, all that to say that if the depth is x, the width of one of our rectangles is going to be 4/5 x plus 16. You can check that. You can plug 20 into this. You'll get a width of 60. You can plug 70 into this. You'll get a width of 100. And the integral is set up. And again, the integration itself is not hard. I'm actually not even going to finish the integral this time. Maybe I'll just pull the 9800 out and I'll factor or multiply the x in. And I won't finish that integration. You can do that. And this is just a problem I made up, so I don't even know what the answer is yet. But maybe we'll look at one more example in the next video, and then I'll turn you loose to work some hydrostatic pressure problems.